Hey there. So if you're gearing up for a tech exam or you're just kind of curious about what's really happening inside your computer, you've got to understand the language they speak. Today, we're going to decode number systems. Now, I know that sounds super complicated, right? But trust me, it's all built on a couple of simple rules you already use every single day. Over the next few minutes, we're going to make it all click. Ready? Let's dive in.
Okay, so here's our roadmap for today. We're going to start with the basics, the rules of the game, using the numbers we see all the time. Then we'll jump straight into binary. That's how computers talk. After that, we'll check out octal and hexadecimal, and really, they're just clever shortcuts for us humans. And to finish up, we'll tackle how to convert between all these systems, which is a super important skill, and then do a quick recap so it all sticks.
All right, Section 1. Let's start with what you already know. Before we dive into all the ones and zeros, let's just lock down the main ideas using our regular everyday numbers. Seriously, once you get how our system works, you've basically got the key to understanding any number system out there.
Okay, so the first big rule is something called the base, or radix if you want to get technical. But really, it's just a simple idea. How many unique symbols does a system use to count? Think about it. For us, it's base 10, right? Because we use 10 symbols, 0, 1, 2, all the way up to 9. That's it. Every single number you can imagine is just a mix and match of those 10 symbols. Understanding this idea of the base is honestly the first major step to getting all of this.
All right, now for the second key concept, and honestly, this one's a game changer. Positional notation. This is like the secret sauce that makes all modern numbers work. All it means is that a symbol's value isn't just about the symbol itself, it's about where you put it. You know, the 9 in the number 900 means something totally different than the 9 in, well, the number 9. And that's all because of its position.
And this image just lays it out perfectly. Take a look at the number 427.5. That 7 right there, it just means 7. Simple enough. But look at the 2 just to its left. It's not just a 2, is it? It's in the tens place, so it means 2 tens, or 20. And the 4, that's in the hundreds place, so it means 4 hundreds. See? That's positional notation right there in action. Same symbols, totally different values, all depending on where they are.
So here's the math behind the magic. Each of those positions is just a power of the base, which for us is 10. The spot right next to the decimal point, that's the ones place, or 10 to the power of 0. The next spot over is the tens place, that's 10 to the power of 1. Then you've got the hundreds place, which is 10 squared, and it just keeps going. This whole powers of the base idea is the universal rule, and you're going to want to lock that away because we are absolutely going to see it again.
Okay, Section 2, binary. So, why do we even need another system? How does this all connect back to computers? Well, think about it. We use 10 different symbols, from 0 to 9. But a computer is, at its heart, a very simple machine. It's basically made of billions of tiny switches. Trying to get a switch to reliably hold 10 different positions, well, that's just not practical. This physical limitation is exactly why computers needed a whole new way to count.
And there's this great quote from the Navy's training materials that just hits the nail on the head. People and computers do not normally speak the same language. And that's really the core of it, right? We've got this communication gap. We're talking in base 10, and computers, well, they need something way, way simpler.
So what is that simple language? It comes down to this. A computer only understands two things, on and off. That's it. There's no maybe, no kinda on, just two possible states. So if we're going to talk to a machine that only gets two states, what do we need? A number system that only has, you guessed it, two symbols.
And this simple circuit shows you exactly what's happening in the real world. When the switch is closed, electricity can flow through. That's the on state. We call that 1. When the switch is open, the electricity stops. That's the off state. We call that 0. And right there, that's the bridge. That's how we connect physical electronics to the abstract idea of numbers.
And that brings us to the binary number system. It's a base 2 system, which just means it uses only two symbols, 0 and 1. But here's the coolest part. It uses the exact same rule of positional notation that we just talked about. The only difference? Instead of powers of 10 for each position, we use powers of 2. So you have the 1's place, which is 2 to the 0, then the 2's place, which is 2 to the 1, then the 4's place, the 8's place, and so on. See? It's the same logic, just with a different base. You don't have to learn any new rules.
Okay, on to Section 3, octal. So, binary is perfect for computers, right? But for us humans, well, reading a giant string of ones and zeros is a recipe for a headache. It's so easy to make a mistake. So some smart folks came up with a better way, a kind of shorthand to make our lives easier. And that's exactly what octal is. It's not some weird new system for computers, it's a tool for us.
So the octal system is base 8. That means it uses 8 symbols, 0 through 7. But you might be wondering, why 8? What's so special about that number? Well, here's the magic trick. 8 is a power of 2. Specifically, it's 2 to the power of 3. And that direct link back to binary is the entire reason octal even exists. It's another one of those perfect bridges between our brain and the computer's logic.
And because 8 is 2 cubed, it means that every single octal digit lines up perfectly with a group of 3 binary digits. So what you can do is take some ridiculously long, ugly binary number, break it up into little groups of 3, and then swap out each 3-digit group for one simple, easy-to-read octal digit. It's just a compression tool for our eyeballs.
All right, section 4, hexadecimal. So octal is pretty neat, right? Grouping by 3s is a good trick. But what if we could make those long binary strings even shorter and easier to manage? Well, we can. And that brings us to hexadecimal. You've probably seen this one around, even if you didn't know what it was. It's used all over the place for things like color codes on websites or for locating things in a computer's memory.
Hexadecimal, or just hex for short, is a base 16 system. Now wait a minute, we only have number symbols for 0 through 9. So how do we get to 16? Easy, we just borrow some letters. So after 9 comes A for 10, B for 11, C for 12, all the way up to F for 15. And why the number 16? I bet you've already figured it out. It's another power of 2. 16 is 2 to the power of 4.
And that relationship, that 2 to the power of 4 thing, is the superpower of hex. Just like octal let us group by 3s, hex lets us group binary numbers into chunks of 4. Each group of 4 binary digits translates perfectly into one single hex digit, and that is incredibly efficient. Think about it, an 8-bit number, which is pretty common, can be represented by just 2 hex characters. It makes things so much cleaner.
Okay, time for section 5. We've talked about what these systems are and why they exist. Now let's get our hands dirty and talk about how to actually use them. Knowing how to convert from our normal decimal numbers into these other systems is a critical skill, and it's something that is almost guaranteed to show up on your exam. So let's nail this down.
So here's the simple recipe for converting any decimal number into binary. It's called the division remainder method, and it's super straightforward. Step 1, take your number and divide it by 2. Step 2, write down the remainder. It's either going to be a 0 or a 1. Then you just keep doing that over and over with the result until you get down to 0. Now, here's the most important part, the step everyone forgets. You have to read your list of remainders from the bottom to the top. That's your binary number.
Let's walk through an example together. We want to convert the number 23. Okay, so 23 divided by 2 is 11, with the remainder of 1. Got it. Now, we take the 11. 11 divided by 2 is 5, with a remainder of 1. Okay, 5 divided by 2 is 2, with another remainder of 1. Next, 2 divided by 2 is 1, with a remainder of 0. And finally, 1 divided by 2 is 0, with a remainder of 1. Now, remember the rule. We read the remainders from the bottom up. So that gives us 1, 0, 1, 1, 1. And that's it. 23 in decimal is 10111 in binary.
Wow, okay, we have covered a ton of ground. So before we finish up, let's do a super quick recap to lock in all the key ideas. This is the stuff you'll want to have memorized. All right, ready? Rapid fire recap. Base, or radix, that's just the number of symbols the system uses. Positional notation, this is the big one, where a symbol is matters. Binary, that's base 2, the fundamental on and off language of computers. Octal, base 8, our handy shorthand for grouping binary digits in 3s. Hexadecimal, base 16, the even more compact shorthand for grouping binary digits in 4s. And last but not least, MSD and LSD. That's just most and least significant digit. The MSD is the digit on the far left with the most value, and the LSD is on the far right with the least. Got it? Good.
Okay, it's your turn. Time to put what you've learned to the test. Here's your first practice question. I want you to convert the decimal number 105 into its binary equivalent. Go ahead and use that division remainder method we just walked through. You can pause right here, grab a piece of paper, and work it out. The full solution is available in the source material for you to check your answer.
And for your last challenge, let's try a little binary addition. add the numbers 1011 and 1101. Now, the rules are almost the same as regular addition, but there's one little trick. In binary, 1 plus 1 equals 2, which is written as 10. So you write down the 0 and carry the 1, just like you would in decimal. If you need a refresher, there's a perfect example in the source material. So now that you've got a handle on the basic language of computers, it makes you wonder, right? What other huge, complex ideas in computing are all built on these same simple rules? Something to think about. Thanks so much for tuning in.